I have to go this way. That's so weird. How does this flip backwards?
I was like, maybe
no, it's on the other side.
How many cameras on the other side?
1, 2, maybe 2.
Just the one.
Oh, there's only one. This one's like sensors, I think.
Oh, interesting. So this side is over there.
No, this one is over here. Yeah, camera's over there. Okay.
What the heck? The sink is not here.
No, the board.
She's not here.
Oh, you're right. She's. Oh, so it is the same. Okay. Oh, she's gonna write backwards, and then I'm gonna see it.
Huh?
She's gonna write on that side of the board, right?
Oh yeah.
Yeah. On that
That's
side of the board.
Crazy.
Thank you.
Oh wait, we're live.
We are live. I am.
So let's get started. So as you saw on the syllabus, we're doing chapter 18. And you might say, why did I skip all of these chapters? First of all, because these chapters are kind of easier, less reactions, and then the others are related to each other, so I just left them at the end. So, but before we start chapter 18, we need to talk about, because 18 talks about benzene and substituted benzene, which is an aromatic compound. So first of all, what is an aromatic compound? Because you heard about aromatic, and it's part of chapter 8, so I want you to go back, check the section 15 to 20. So if you want to read about aromatic compounds, it's from sections 15 to 20 of chapter 8. So what does it take to have an aromatic compound? You have to have 3 things. So I'm going to put the three conditions. It has to be cyclic, means a ring, and it has to have a planar. The structure must be planar, and it has to be conjugate and non-interrupted. So I'm going to give you a few examples to understand, okay? Basically, I think benzene is the ideal example. Benzene has this structure. So you have the p orbital here. Remember, to make a pi bond, you need to have a pure p orbital. You can't have a pi bond with hybrid orbitals. So these are the p orbital, and each has 1 electron. So I'm going to use the green and then the blue just to give you the 2 options. So one option would be this bonds with this bonds with this bonds with this. You know how pi bonds are side by side overlap, so they bend and touch like this, the p orbital. Or we have here, I'm showing the blue in the bottom, but it doesn't mean that normally it should be top and bottom at the same time. So maybe I should do this. Don't get confused. So these orbitals kind of bond like this, but the other option would be instead of these two bond together, these two. And then these, and then these. So these are the 2 resonance forms of benzene. The way we write it, we write, and then you see little dots like this in some of the books. So what does it mean? It means these electrons are constantly running around in a circle. They never stop. And you see that since every single one of them is sp2, sp2, it's planar. So it's trigonal planar. It is cyclic, and it's conjugated non-interrupted, meaning the electrons don't stop. Also, actually, these are called aromatic, meaning like they have these 3 conditions. And then another important thing is that they follow the Huckel's rule. So what is the Huckel's rule in terms of electrons? So it says to be aromatic, you have to have 4n plus 2. I'm going to explain what it means, 4n plus 2. These are the number of pairs of electrons. So if n is 0, what is this? 2. So that means you can have two electrons, which means 1 pair. N equals 1, it's going to be what? 6 electrons, which means how many pairs? 3. So it has to be an odd number. So if n equals 2, it's going to be 10, which makes it 5. So it has to be an odd number of pairs of electrons. So these are your 4 conditions. So don't forget, it has to be cyclic, it has to be planar, it has to be conjugated, and it has to follow Huckel's rule. So to see this, let's put a few examples. So, what do we have here? It's cyclic. You read how many pairs of electrons we have inside the ring. So,
1 pair.
1 pair. But you can see that this is an sp3. So this is uninterrupted. So although it's cyclic, although it's planar, so this compound, you need to know that this is cyclic, it is planar, and it follows the Huckel's rule, but it's interrupted right here, meaning the electron cannot go through this. This is an sp3. You can put the electron there. Let's look at this. This is cyclic. This is planar also. How many pairs does it have? How many pairs of electrons inside the ring? Do you understand what we mean by pair? This is a pair. So, how many pairs?
1.
So it applies, it follows the Huckel's rule. Is it conjugated or not? What does it mean, conjugated? This is the key thing. When I represent it in slightly in perspective like this, so we have, these are the 3 orbitals, okay? 2 of them are making pi bonds. But this is a plus. What is the hybridization here? What's the hybridization here?
Just sp3.
What's this?
sp3.
And this is? So this is sp2, but it's empty. So what can happen here? The electrons can also move. That's called conjugate. Okay, so we can write another structure like this, where the electrons are attached this way, and this is positive. And this is positive. So that's conjugated, and it's also non-interrupted, so it's perfectly conjugated. So is this aromatic or not?
Yes,
Yes.
aromatic.
How about this?
Yes,
This, it is cyclic, yeah,
it is planar.
Mhm.
it is planar. But this, I put it here, can also be where? inside. So how many pairs do you have here? 2 pairs. This is part of the ring. So here we have 2 pairs. Is that good? No, so that's not aromatic. Okay, let's try a few more.
Professor,
Yeah,
if those electrons move into the ring, the other electrons have to come up.
which one?
The extra
Can be
electrons there,
moving.
they don't have, if they move in, the pi bond have to go up onto the carbon.
You have to have 1 electron per orbital to make 5 bonds. You can't have 2 electrons per orbital. Here we have 2 here, there's no electrons. So they can kind of like switch. The distance is so close that they can move around. In here, they can move, it's full. The orbital is full, so there's nothing to get moved. Okay, so here are a few more. These are important. This one. So it looks like benzene, and it looks like we can make 5 bonds and they can switch around. You agree or not? They can totally switch around. But what's the problem with this? 4 pairs. Now, why is that? The minute you put 4 pairs, this is no longer planar. It becomes kind of like in 2 steps. Okay, so it switches up and down, up and down. So this is not aromatic. Okay, it's not aromatic. So what does it mean if it's not aromatic? It means the reactions we study in this chapter don't apply. So why is it important to understand aromaticity? It really has to do with what type of reactions we're going to study. If it's aromatic, everything we studied for benzene applies to aromatic compounds, everything. If it's not aromatic, then it doesn't apply. So this becomes more of alkenes, conjugated alkenes. So this is not aromatic, it's more of a conjugated alkene. And which chapter talks about conjugated alkene? Remember? Chapter 7 or 8, I don't remember, one of them. But that's what a conjugated alkene is. So if it's not aromatic and you have pi bonds, they're conjugated, you have different type of reactions. Okay, a few more. It is cyclic, you agree? It is planar. Why? Then because you have the Harcourt rule, HR I should put that. Harcourt's rule, because we have how many pairs here? 3 pairs. Now, is it conjugated? Yes, because the resonance form here, you can move this here, okay? And you have this. Now this becomes positive, and it keeps going like this. And then it keeps going like this. Then you get back. And then the last one. So this is why you had to learn how to write resonance forms. So this is now the positive center. And then we have double bond here, 1 here. one here. We're not done yet. You understand that we're not done yet? Because as long as it blends to a different structure, you still keep going. So this can move over here. And now I'm doing this on purpose to show you something that we will mention, okay? So now this is positive. And then this moves here. This is positive. And then now this moves here. And then we can do that first. Now, so what does this mean? Is this compound is definitely aromatic, and it has how many centers that are positive? How many positions are positive?
7.
7. So every carbon has the potential to accept something what? Something negative, a nucleophile. Okay? So we're going to look at this in this chapter. So is everybody understanding aromaticity? You have to have an odd number of lone pairs. Actually, I'm going to do another one because it's related to chapter 19. So here we go. Is it cyclic? Okay. How many pairs?
2,
How many?
3.
3. Is it planar? Yes.
Yes.
So is this aromatic?
Yes.
Absolutely. Yep. So what are the resonance forms? You move this over, and you don't do it several times. Do one at a time. You don't do it all concerted all at once. You only do concerted if you have the same atoms all around. Okay, so I'll show you with benzene. Now, you need to do a tutorial for this resonance forms. If you don't know how to write them, you're going to be in trouble, especially next week, because they are major in next week's lecture. Okay? So where is the tutorial? It's right after chapter 8. I want you to try all the questions, and they have answers for them. So that's the cool thing. It's on page 2. Please write it down. I'm telling you right now. It's 225. It starts at page 225. It says writing curved arrows. Actually, no, that's not resonance forms. What am I talking about? Let's can start with that. There's another tutorial after chapter 8. 382.
Yeah.
So it's 382. Yes. Okay, so page 382, you have many questions, and they give you the answer at the end. So make sure you try it. Okay, so here we move that one. So now we have a double bond here, and this is positive. Okay, the next step would be what? So you see I moved there. I can also move the lone pair here. Not on the atom, it's on the bond, just to show it's making a pi bond. So when it makes a pi bond, you land it in the middle of the bond. When it lands on an atom, you put it on the atom. So it's important, these details. Okay? So now this is positive. Yep. Any more structure? anymore? Can go back. So this goes back here. And then you go back to this. Okay? So that shows that you have 3 centers. 3 resonance points. Another one, last one, is this. How many pairs are in here? No, only 3. This one is now outside. Why? Why is this outside? How do you know it is for sure outside? What's the hybridization here? SP2. So what's the shape? Trigonal planar. So this and this and this are in what? 120. So this must be outside. It's not inside the ring. Okay? But this is definitely aromatic. Okay? So we're going to study this in the next chapter. And you have lots of questions on chapter 8 about aromaticity. So if you want to practice, I'm not sure, but I think I put some answers for these questions. I can tell you right now. There's problem number 50 and 72, chapter 8. Okay? So this chapter focuses on benzene. Let's look at the average structure of a benzene. So when you write it in this position, you all learn that the double bond is shorter than a single bond. Then we can write them something like this. This would be the double bond. Now these are the 2 forms of benzene. And we know that it's not going to be either one of them. Why? Because if this is the correct form, this bond would be shorter than this. If this is the correct form, this bond will be shorter than this. So what is observed is the bond is never going to be as short as a double. It's not going to be as long as a single. So it's something in between. And that's the reason they put little dotted lines. Okay? So the proof is there that benzene doesn't have double bonds, doesn't have single bonds. It has something that is, all the bonds are identical, and all of them are somewhere between a double and a single. So they're not as short as a double, and they're not as long as a single. So that's the first thing to know. And the molecule is flat. The second thing to know is, if you have to bring any kind of reactant, which spot is the one that's weak? Which place of the compound is the weakest spot? There's no reason, you agree? There's no particular spot because all the bonds are non-polar. So you learn that when we studied alkanes are very non-polar. The only reactions they undergo is radical reactions with halogens. Remember? So this is the same thing. Benzene is dangerous. You might say, hey, how can it be dangerous? It's a poison because it is, it's not polar, but it's definitely also not reactive, except when you have it in your body, then it starts doing crazy stuff. So we'll see why. Why it reacts in a weird way in certain environment, whereas when you just look at the structure, benzene is unreactive. Okay, so everybody understand, benzene doesn't react. But another thing about benzene is you see here, the atoms are in the middle, and you have these pi bonds, so you have electrons hovering above and below. So benzene is used in conductors. You know, the conductance. Now the material science, for those who are interested in material science, what they do is they create many benzene rings attached to each other, and you have all these cloud of electrons circling around and around. So they have very interesting properties. You know, you learn about some kind of crystals that are used in calculators, in watches, and now they're using a lot of this in new computers and new technology because of these electrons floating around and around. So benzenes are nucleophilic. So please remember that. Nucleophilic because they have these flying electrons on the outside. Everybody understands what it means, nucleophilic. It means they're electron rich. They're slightly negative. Not really, but the electrons are exposed. That's what we mean. The electrons are on the surface. So because the electrons are on the surface, the only kind of reaction we can do is what? Can I bring more electrons to a benzene ring? No. So all I can do is bring something positive. Okay? So benzene is very n-reactive because it's very nonpolar. But if it reacts, it's going to react with what? So what do we call the things that are positive? Electrophiles. Okay? So what are the possible reactions? I'm going to give you here two options. So here's the benzene. And an electrophile, we use here Y+. Okay? The book uses that, so I want to be consistent with the book. Okay? So when I put Y+, you might think it will add. So I'm just going to put here a hydrogen. So you know that there is a hydrogen right here. And I'm going to put Y+. So the possibility would be a pi bond attached takes the Y+. Okay? Because the electrons are on the surface, so that electrophile might grab the electron. Okay? So you end up with this. You have now H and Y. Now this one is now positive. Are you seeing this? Once the Y docks onto the benzene ring, one of the carbon is now positive. Now, what are our options? Either, after this, what can we do?
Eliminate your hydrogen.
Either eliminate or we can add something negative. Okay? So if it's an addition, remember how alkenes are, they do addition? Addition, you always add two atoms. Okay? So let's say, what type of atom can we add here? Is it something positive or something negative? Negative. So we're going to bring a base or nucleophile. Okay? So this is one option. I'm bringing the base, and the base will attach here. And we end up with this. Y, H, B, and then this. So this would be an addition. Okay? Now something that is observed is that benzene will never undergo addition, no matter what. Why? What did we start with here? What type of substance is this?
Aromatic.
Aromatic. What happened here?
Lost it.
Lost it. So this would never happen. You can never have a reaction where an aromatic becomes non-aromatic. It never happens. You have to take very extreme conditions to make it work, which is not worth it. So you can, but it's really not something that happens naturally. So again, this is not going to happen. Is everybody understanding why? Because we go from what? Aromatic to a non-aromatic. Anytime you have something like this, remember, it's not going to work. So what is then the other option? Benzene cannot add. So all it can do is we have to touch a pi bond, no matter what. We have to do the first step. Okay? I still need to bring an electrophile. So the first step is the electrophile attaches. That's for sure. It will happen. But it's not very stable, so you know why. The energy profile of a reaction. So this would be an intermediate. You have H and Y, and this is plus. The only option now is to regain aromaticity. So what do I need to do to regain aromaticity? Eliminate an H. I'm just showing you so you remember it. You understand why you have to do this. Okay? So what does it take? A base again. You have to have a base. And that base will grab the H. This would be easy because this produces an aromatic compound. So the first step is very hard, but the second step will be very easy to do. And then you end up with an aromatic compound. And then we have a Y plus pH. So the energy profile of a reaction like this would look, the first step, benzene is very stable. Understand, it's really like a stable compound, aromatic, everything is happy. You have good bonds, everybody's happy, it's cyclic. And then to create that intermediate, you really need a lot of energy. You agree? That's called what? Activation energy. And our first intermediate is what? So that one, which is no longer what? Aromatic. So that's why it's going to be pretty high. But then the second step will happen so fast. When it's fast, what do you have? You have a small activation energy. So this would be the profile. This won't happen. So the good news is, as I said, if it's not reactive, then we don't have that many reactions. But at the same time, you understand that you need to really, to make these work, you need catalysts. They're not going to work without catalysts, no matter what. So benzene, being not very reactive, requires a catalyst. And for you, all the mechanisms are the same, except that what type of electrophile can we use? That's the only difference. All the reactions, so this is an addition, it's not going to happen. And what is this called then?
Yeah, elimination.
If you look at the before and after, what happened? Substitution. But it's a very special type of substitution. You agree? What type of substitution is this? It's an addition elimination. But it's really, the name of it is substitution. And it's called electrophilic substitution. Why is it electrophilic? Because we need an electrophile. So benzene will only undergo electrophilic substitution, but what is the process? Is always two steps. The first step is what? This one is a addition. And the second step is elimination. So you add one atom, you eliminate another to end up with a substitution. And from now on, from this chapter on, you're going to see a lot of substitutions like this. They don't happen like chapter 9, where substitution happens through a carbocation. It's only a substitution. Here, it's never going to be only a substitution. It's always going to be addition, elimination. So that's the difference. Okay, now what type of reactions do you have with benzene? Good news is there are only 4. Okay, the first one, and they don't have to be in order, but I'm just going to tell you what they are. The first one is halogenation. The second one, so what does it mean, halogenation? The benzene here, the H, becomes a halogen. The second one is nitration. Third one, sulfonation. And the last one is Friedel-Crafts. Now, Friedel-Crafts has 2 subcategories. Okay, so within 4, we have A, alkylation, and B, acylation. So we'll write, for nitration, actually, this turns into this. For sulfonation, you turn it into SO3H. For alkylation, you put an alkyl group. And for acylation, you end up with an acyl. Now, since all of them have pretty much the same mechanism, why then should we study 4 of them? Okay, if they're the same, you just say, okay, you learned one, it applies to all of them. Well, the answer is they're not exactly the same. So what I want you to know, and when you study this chapter, is always remember, how are they similar? How are they different? How are they similar? How are they different? In other words, what are the limitations of some? What are the exceptions? Why do we need, let's say, alkylation, acylation? What is the purpose? Okay? So let's start with halogenation. So if I put benzene, Br2. Can this work? Let me see if you can think. No. Why not?
You tell us.
Even if the first thing is, you put this, what do we have here? Coming out here. Electrons. When I put this, what do we have on the outside? Will they ever react with each other?
No.
Absolutely no way. Okay? So You just put the two of them, they will be completely staring at each other, nothing will happen, nothing. So what does it take? We need to create what? We need an electrophile. But what is the electrophile here? If I call it bromination or halogenation, what is the electrophile? It's the halogen. So how do you make a halogen positive? You understand what I mean by that? To have a halogenation on a benzene, you have to have a positive halogen. Because we already established we can only bring something what? Positive. And of course, we also need a catalyst, but the catalyst is either to activate one or the other. You activate one of the reactants, the reaction will happen. Okay? So how can I make a halogen positive? You all know halogens are non-metals. Okay? The reason I'm saying this is because when we get to chapter 11, you're going to start to remember again. You will see that we have tools to make atoms that normally are negative to make them positive, and atoms that are normally negative to make them, the negative becomes positive, the positive we can make them negative. So we have to think of how can we do that, okay? So the way it works, you bring in here, they tell you for these reactions, you just need iron bromide. So if I take the halogen as bromine, I'm going to take FeBr3. FeBr3 is cheap everywhere, and today you use FeCl3, yeah, in the lab. So this is FeBr3. What is going to do? What is FeBr3 going to do? And you notice what I did. What did I put here? What did I put again? Empty orbital. So it's to show what?
It's gonna accept. It's gonna accept the electron.
It is what?
Lewis acid.
Lewis acid. Okay, so now I bring Br2 here. I'm going to forget about the benzene now, because the benzene is not going to touch the bromine until we prepare the bromine. You understand this? So this is the key thing about these reactions, is how do you prepare your electrophile? Because if I'm going to put sodium, sodium is an electrophile, but is it any one of these? Do I care about sodium attaching here? Well, all electrophiles that are easy to make are metals. You know that. All metals become positive. So it's easy to attach any metal on the benzene. So we think, we're not sure. But here, to create any of these, every single one of them must be positive. So how do you make it? In here, for bromine, you put FeBr3 Br2. And notice, if I show this mechanism with all the dots, I expect you to show me all the dots. Don't put me charges. Charges don't move. Electrons move. So if you put a negative charge, and I saw some of you in previous classes, nobody paid attention to that. They just accepted. I don't accept that you make charge move. It's electrons that move. So this bromine will dock into this orbital. So immediately, if I bring it here, it shows that now these two electrons are completely on the bromine. Now they're like shared. So what happens to the charge of this bromine already?
Positive.
Hmm?
It's positive.
Positive, absolutely. It becomes less negative because it gave some of its electrons. Sometimes I don't look here, okay? Sorry if I look like I'm not paying attention. So what we have here is Fe, Br3 on one side, okay? And then on the other side, we have a Br and a Br. Okay? The iron added another charge, so this is negative. You agree? It added another pair of electrons. And the bromine here, this one, is positive. It's this one, the middle one. So now we created a shift in the bond, so the bond becomes weak. Okay, so that's when you bring your benzene right here, which bromine will attach to the benzene?
All right.
Well, really, what happened is this. So remember, bromines are also Lewis acids because they're from period 3 or higher. I'm just shifting a little bit the electrons, a little bit here. So this one has an empty orbital. It has the d orbital that's empty. So what happened is this benzene takes this, because first of all, this is more accessible, less steric hindrance. So it's always the last one. But once this takes this pair, oops, this now moves to this. So it's not the middle one. The middle one is out of reach because it's too crowded around the middle. Yes.
Why are the beginning the electrons of the benzene ring attached to the lone?
Because it's symmetric bond, completely non-polar in a Br2. In here, the minute we added the iron, what happened? It shifted. Very good question. For bonds to break, you have to cut that polarity. You have to change it. The non-polar must become polar. Otherwise, the bonds are not going to break. Any non-polar bonds are very, very hard to break. Okay? So Br2 is totally non-polar. The minute you dock it onto the iron is going to be very big compared to the bromine. It shifts the balance, and that creates a polarity. Okay? So then now, what do we get? We get this. Now you see the bromine let go of that, so now it has 3 pairs, which is fine. Okay? And then this is positive. And then what we have FeBr4 minus. If you don't keep track of your charges, you're not understanding what's going on. Okay, so what happened next? What's the second step? This was the hardest one. What's the second step? Elimination. So what's going to eliminate the H? FeBr4 minus, the H will go with the Br and it takes off. So we can show it here. So we can put FeBr3 here, minus. Okay, so what's going to happen is the bromine takes the H, this goes here, and I missed the counter bond there, and you end up with your brominated benzene. And since this is a catalyst, what is it going to do? Start all over. So that's a good mechanism when you show that you're regenerating your catalyst. So is everybody understanding this? What's the key thing in this process? The key thing is to destabilize the bromine and make it electrophilic. Okay, just want to make sure I'm not forgetting anything. So now how does this work? It works with bromine and it works with chlorine. We don't use fluorine. Fluorine is extremely reactive and you can control the reaction. Okay? So I'm going to tell you the limitation here. So the halogen, if it's chlorine, you use FeCl3. If it's bromine, you use FeBr3. Why? You don't want to mix halogens. You understand? So whatever catalyst you use has to have the same halogen as the one you want to add so that you don't get byproduct or side products. Iodine doesn't work with iron because of size, okay? So they're not very compatible. So the best method for iodine is not to use this mechanism. For iodine, you use hydrogen peroxide and water. So you have to oxidize it, okay? And you don't need to know all the mechanisms. You have water and you have sulfuric acid. So that's going to give you I+. The only way iodine will let go of its electron is with this. You get 2I+ plus 2H2O plus HSO4 minus. Now, what are the limitations of this reaction? These are very reactive. When you start putting bromine and iron bromide or chlorine and iron chloride, they're very reactive. So the reaction doesn't stop once. You're going to have the first halogen and then the second and the third because the halogenated become reactive. So that's the limitation, and we're going to talk about that next week. So make sure you write it down. What happened here is once you brominate once or you halogenate once, it doesn't stop. It keeps on going. So if you want only the monohalogenated, if I want only one time it halogenated, it doesn't go again and again and again, what should I do?
Limit the amount of doses you have.
Absolutely. So write it down. If you want only one monohalogenated, you have to limit the amount of halogen and put a large excess, the benzene. So benzene must be in large excess, and the halogen would be very limited amount. So it can be 1-to-1 ratio. You put 1-to-1 ratio, the reaction goes crazy. And you're going to end up with many, many products. So you have to have the benzene in large excess and the halogen in small amount. So that covers halogenation. Okay, now we're going to go to nitration. So as you can see, nitration, we use nitric acid. So what is nitric acid? What type of compound is this? So nitration, put NO3, sorry. What type of substance is this?
Base.
Hmm?
The base.
The name is nitric acid,
That's this.
but what type? That's the specific. Bronsted acid. So if it's a Bronsted acid and it reacts, which part is the electrophilic? Which part is the positive part of an acid? Hydrogen. But what did we put? NO3. And you all know NO3 is always what? Negative. But here it must be what? So how do we make a strong acid become a base, literally? Okay? And that's what you need to understand. Bronsted acids don't react with benzene. Why? It's not like they don't react. What's going to add if I put a strong Bronsted acid? I'm removing an H and I'm replacing it with what? An H. So is that a reaction? That's what I want you to remember. Why are we using Lewis acids, not Bronsted acid? A Bronsted acid will remove an H and put another H. So that's not interesting because we're not substituting anything. So you always have to work with the fluid acid. But here, we need a catalyst. So the only way, I can't put iron here because it's not gonna work. Iron will suck all the NO2 and keep it. It's not gonna let go of it no matter what. So there are some elements, when they're too small, they stick to the metals and they can be removed. So here, you can't use iron, you can't use metals. So what are we gonna use? It's sulfuric acid. An acid with an acid, which is crazy, isn't it? One will react as the base, the other one will react as an acid. So the way we write it, we write HONO2, and then in the presence of sulfuric acid. So the first step is this takes the H, this takes the lone pair. SO3, thank you. And then we're going to end up with OH, H plus, and then NO2. Okay? So I was right, it was NO2. Duh. I don't know why I'm thinking that. And then this with SO3H minus. So now at this point, this opens and this attaches to the benzene. Okay? So at this point, you're going to end up with H2O plus NO2. So nitric acid will do this if you put in the presence of sulfuric acid. Nitric acid will react as a base. Sulfuric acid is so strong that it makes the nitric acid be a base. And then at that point, then you bring your benzene, and that now can take the NO2. And then we still have the OSO3H minus, which is gonna take the H and folds, and you would regenerate your sulfuric acid. Remember, sulfuric acid is just a catalyst. So this is called nitration. The next one is sulfonation. Now, what is the difference between nitration and halogenation? Because remember, I asked you to remember what are the similarities and what are the differences. Already in here, we know the catalyst is what? An iron atom. In here, the catalyst is H2SO4. Okay? So sulfuric acid here is the catalyst. And what did we say about this one? This can go more than one halogenation. So what do we do to limit the amount of halogenation? Limit amount of halogen and put a large excess of benzene. In here, it doesn't go more than once. And you get, this is working, but it's not working the way you think it should work, you know? It's still two acids, okay? So there's still two strong acids, so it's gonna be not an easy process. It happens, but it's not something that goes straight forward and everybody's happy. Nitric acid is gonna struggle with sulfuric acid. Each one will say, I don't give mine. I take yours, but that's in the end, the sulfuric is slightly stronger. So this only goes one nitration. And we will see later why also this substance has hard time reacting again. Now, the next one is sulfonation. Sulfonation, instead of using sulfuric acid, nitric acid, we're going to use sulfuric acid. So in this case, one is the base, one is the acid. So it's within the same molecule. So here, we end up with, so it's SO3H. So here, it will be SO3H plus. So this would be SO3H. And this would be SO3. So they're both exactly the same. One is autocatalyzed, like the sulfuric acid catalyzes itself. The other one is sulfuric acid is the catalyst and nitric acid is the. So you already can see why this is not going to give you high percent yield. It might give you some of this too. Do you understand? So if you put too much of the sulfuric acid, you're going to end up both with sulfonation and nitration. Is everybody understanding this? So the sulfuric acid can react with nitric acid, but it can also react with itself. So you're going to end up with low percent. Now we go to Friedel crabs. Friedel crabs are very different creatures. You're good with this? Okay. Oh, and I forgot to mention something, by the way. This sulfonation here, it is reversible. So why is it reversible? Because the SO3H gives SO2 and water, so the gas will escape and it's reversible. So that's the problem with sulfonation. It's very difficult to do. You need heat, but when you heat it, the SO2 is released. So just keep that in mind. This one, low percent yield because you can have also sulfonation. And this one is reversible, so it's not always a good choice. Okay, so let's look at Friedel-Crafts alkylation. Yes.
Real quick, how do you reverse it? I know you said that when it turns into gas releases water.
So
you
it's
just heat it?
it just heated, yeah,
Okay.
with heat. And also, I tell you, the acid itself will react with this and remove it. So you don't have to know the exact mechanism even though it's written in the book,
No.
but what also is with that is now sulfuric acid. So that sulfuric acid will activate with the heat the SO3, make SO3 gas and a benzene again. So it kind of goes back and forth. So that's why they're not very good. None of them are good. This is too reactive, so you have to slow it down. This is going to give you a side product. This is reversible. Okay? So these are the keywords to take with you. The top one is too reactive. It's hard to control. The second one is gives a low percent yield because you have side products. This one. And the third one is also gives you a low percent yield because it is reversible. So it's going to be hard to produce that sulfonated benzene. Now Friedel-Crafts. So I'm going to start with alkylation. So what is alkylation? They have this plus Rx produces that looks in a perfect ideal world, that would look perfect, isn't it? Why? Because you all know when you have an alkyl halide, the halogen will take the electron. So this would be the negative pole, this would be the positive. So in terms of reactivity, see, this is the negative, this is the positive. So this is definitely an electrophile. This bond, you can break easily, but this one is not easy. So how do we put them together? What do we need here? Every time, so one is polar, but the other one is not. So what do we need? The catalyst. So what is the best catalyst here? You still need the Lewis acid. Okay, no Bronsted acid because Bronsted will give you the benzene again. Lewis acid will be with the metal. So here, the best metal is aluminum. Okay, so we do chlorination, so we're going to use aluminum chloride. So first of all, you take AlCl3. Okay, so AlCl3 is also the Lewis acid. Aluminum is from period 3, so it has empty d orbitals and some of the p orbitals, and you name it, it has enough orbital. Then you bring an RCl. So I'm going to use this one for now. Simple. Okay, methyl chloride. So just like in the previous scenario, the chlorine, and in 201 they talk about this complex of elements with the aluminum. So you end up with a CH3, Cl, Al, Cl3. So you already know this is negative, and this is now positive. Okay, so what's the purpose of this? You might say, okay, the CH3 can leave, but by creating this bond, it will be even more positive. It's like a real strong pull. So that pull will force this to attach to the benzene. Okay, so your benzene here will take the CH3, and then this goes here. Okay? It's always an addition first. And then we have the Cl, Al, and Cl3 minus. So this takes this folds here. Actually, not this way, sorry. This takes this. So you end up with the alkylated benzene. Plus HCl. H from the benzene, Cl from the alkyl halide. So the alkyl halide gave its chlorine, the benzene gave its H, and they kind of switch partners. Yes?
Why does the benzene attack the methyl group and not the?
Because just like we did earlier for bromine, first of all, this is hidden. It's in the middle. You have a lot of steric hindrance. And this bond is more polar than, you have to break a bond. It's not about just the atom, you have to break a bond. So which one is the most weak? You have to break that bond. Yes,
I noticed in these reactions, like you're drawing it, the pi bond is directly going from from the middle to the proton. Is it okay to have it from the chlorine's electrons and then have the pi bond go to the chlorine?
which one you talking about?
So say this middle one, the chlorine's
No, you
electrons go
can't,
to,
this one is the one that breaks, not this one. You have to break a
Yeah.
bond to create a bond.
but I'm just saying if the electrons go to the proton, right? And then the pi bond goes to the chlorine. You're saying it directly happens at the same exact time?
Which pi bond, you talking about this one?
Yeah. the
There's
same
no
one.
pi bond here, this becomes a
Oh.
pi bond.
Okay. Sigma bond, between the chlorine and the aluminum, right? If that just
It
goes
can
straight to
go
the
here.
chlorine, no, just to the chlorine that's right there.
I'm sure, I don't understand.
I'm just asking if you can go like this.
No, 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 no. So that's a good question, very good question. So it's asking if, it's pretty much what you kind of said.
Yeah.
I think that's what went in your head. Okay, very good question. What I'm saying here, lone pairs are usually stable. They're not polar, you understand? It's only the weak spots that do the work first. You understand? This is not gonna come here, it's stable. It's this one, because the aluminum is pulling, that one will break. So you only do break bonds to create new bonds. You don't use this. This, you only use it if you're gonna add, if it was negative, like when I have a Br minus and I can add an H, like here. See, like this. But if it's something that has a bond, the bond break before this one even attaches, because that's the more polar.
Okay.
You have to break bonds when you create bonds, okay? If you can, if you can break bond first, that's what happens first. Okay, so it's really only at the last step that you can do these things. Yeah, no two arrows, only one arrow happens, okay? It's because that bond becomes weak that goes there. Okay, so now what are the limitations of this? So here are one thing, here's one thing. If instead of taking a CH3, okay, I use this one. Or even if I use a long chain, I just want to show you something like this, so you don't open. Even if you use a long chain, this step requires a formation of a carbocation. In here, we can only form CH3, you agree? But in here, what type of carbocation? You can have CH3, CH2, CH2 plus, but then you can have hydrogen moving or the methyl group, and it rearranges no matter what. So these, whenever you have a long chain, no matter how long it is, if it's 3 or more, the product is, I'm not going to show the detail. There is a rearrangement, and what you end up with is always a branched thing. Okay, so you can't have something linear and expect to end up with something linear. It won't happen. Okay, so that's what you should write. You don't write the whole mechanism, but you just have to write that when you take a long carbon chain, an alkyl group will always rearrange. Even if it wasn't a normal hydride shift or whatever you know, it's not your normal mechanism, but it will always, always, always rearrange. So that's the limitation. It's like, I can't have this attached here in the way I started with it. It will always rearrange to a more stable carbocation. So what do we do then if I want exactly like this? What if I don't want it to change? And this is where you go to synthesis. In synthesis, what if I want a long chain? I don't want a rearrangement. That's why free Dirac alkylation have limitations. Okay, so write it down. Free Dirac alkylation, the alkyl group will always and I would underline the word always, would always rearrange to a more stable carbocation. The other thing is, it doesn't stop. So it's just like the halogenation. It doesn't stop. It goes twice and 3 times. So these are the 2 limitations of Friedel alkylation. The alkyl group rearrange and the reaction doesn't stop in one time. So what do we do to slow it down to make sure it only works once? Put the benzene in large excess. So everybody's understanding these limitations. So what we have left is the acylation, okay? So what is an acylation? You start with acyl group. So instead of RX, you start with an acyl halide. And an acyl halide, we're going to study them soon, are extremely reactive. So they're cool because they react. Okay? So it's an RCOX, and it produces CO plus HX. That's the overall reaction. So I'm going to use the chlorine, okay? So I have a COR. So the mechanism here is similar to the previous one. Still the halogen attaches to the aluminum chloride. And then you get an RCO, Cl, Al, CO3 minus. This is plus. Just like earlier, you bring the benzene. And the benzene will do this. So now, why is this also easy? Take a look. What type of bond is this? Remember, for bonds, for reactions to happen, you have to have polar bonds. So not only it's polar, but the oxygen can what? Can pull the pi bond to allow the reaction to happen. So that's why we're going to see them in the next few chapters, how the carbonyl group has a very positive carbon. That carbon is more positive than an alkyl, than a carbocation. Okay? So remember, a carbocation, what does it have around it? Lots of carbons. So the bonds are polar. Whereas here, the bonds are non-polar for a carbocation, but here they're very polar. So that carbon is very positive. So this works beautifully. Then we have the Cl, AlCl3 minus. So this again, this takes the H, this goes here, and you end up with the same mechanism. But this reaction requires an additional step. Why? Because the oxygen is very nucleophilic. And this is what? Lewis acid. So guess what's going to happen? This will attach to here. So the carbonyl group can reattach again to the aluminum chloride. So what do? Think of a kid. The kid loves his candy. And I'm a kid, I have all these candies in my hand. And you want to take it away from him. What do?
Beat him up. Give him a toy instead, beat him up.
Give him something that he likes better. Okay, so here, aluminum loves to go to the oxygen. So what do? Give it more oxygen, but which oxygen? Oxygen that's not here. So flood it with water. Do you see? So if you put water there, the aluminum will find, oh, there's a lot of oxygen here. Why should I go and fight for that one? So what you do, the last step here is to add water. For free aircraft acylation, you add water. And what's going to happen, this is not going to work anymore. The aluminum will grab the water oxygen rather than the oxygen on the carbonyl group. And it will produce AlOH, okay, plus HCl. So you see, like, okay, don't take that oxygen here, I'm giving you tons of oxygen. And then you can let go of my molecule, don't touch it. Now, the book doesn't talk like this, but it's really what happens. So I'm trying here to help you all remember these little things, these little details. Okay, so what are the advantages and disadvantages of doing this? This one, we have no rearrangement, but it's a carbonyl. So if I want an alkyl, if I want to remove the CO, we'll study this in a future chapter, that I can remove the CO and reduce it into CH2. So free aircraft is very powerful acylation for two reasons. This compound is not reactive, so you're not going to have a second and a third and a fourth. So acylation doesn't happen many times, it only happens once, which is cool. Alkylation happens more than once. Remember, this is more than once, this is more than once. These don't happen more than once, okay? So this one and this one will keep going. So if they're gonna keep going, it's not a good thing. But the others don't keep going, so that's great. And then finally, you can totally transform this into something like this with reduction. So we'll talk about that next time, okay? Thank you, guys. And I need the attendance sheet. Did you turn it around?
Yeah.